So let's take a real XY coordinate system. This is x-axis and this is y-axis, and this is the origin, and from where I take the straight line with points plotted. Therefore, I take the scaling on x and y-axis with this starting with 1, 2, 3, 4, 5 and 6, etc. and then -1, -2, -3, -4, -5 and -6, etc. And similarly, I get here 1, 2, 3, 4, 5 and 6, etc. and then I get -1, -2, -3, -5, 4, 5, 6, all with minus signs. Then once I get all the scaling done on x and y axis, I first plot the points for the line 1 and then plot the points for the line 2. So initially, to start with, these 2 points, 0, -1 lies 0, -1 comes down because these coordinates move along y-axis and these move along x-axis. And -1, 0, so moving here, -1 and 0 comes here, and 0, -1 comes here. When I just intersect them, I get the coordinates. Similarly, I just join the points. And this is a straight line connecting x plus y plus 1 equal to 0 is the equation of this straight line. Similarly, I draw the straight line this using these 2 points, 0, 5 and -5, 0, which intersect Therefore, I get this line to be x minus y plus phi equal to 0. Therefore, these 2 lines intersect at this point, which gives me the point of intersection of the 2 lines. Therefore, the point of intersection, as we have obtained in the previous case, was 3 and 2, which I got in the case as x 2x equals -6. So x is -3 is what I obtain approximately, because I'm not using the graph paper, so I get the approximation where here the x coordinate will be -3 and my y coordinate will be -3 plus 1, which is 2, which approximately touches here. So this is the point of intersection which I obtain here, and the point of intersection decides the solution of the given linear equations. Therefore, the point of intersection is here P, which is -3, 2. Therefore, this value of x and this value of y will be nothing but the solution of the given linear equations. So for the given 2 linear equations, the x coordinate of the point of intersection, which is -3, and the y coordinate of the point of intersection, which is 2, will be the required solution of the given linear equations, is how we get the solutions. So now that we have connected the graphical method of understanding the solutions of linear equations, both algebraic and graphical method, now this makes me understand finally with my learning outcome that if I find the point of intersection, then the x coordinate of the point of intersection will be the value of x, and the y coordinate of the point of intersection will be the value of y, and which together forms the solution of the given linear equation. Now this makes me understand with different cases of the solutions. Say for example, if the 2 lines do not intersect, then what is the status of the solutions of those 2 lines? If the 2 lines are coincident, then what is the status of the solutions of the equation? If the two lines intersect, then what is the status of the solution? So the different cases arise with different types of intersections, as we see in mathematics. To start with case 1, the heading is nature of solutions based on the shapes of the lines as obtained in drawing on the real xy coordinate system. Based on the trend of the lines, we can decide the nature of the solutions, which is a very important concept connecting the straight lines, the trend of straight lines with that of the solution of the linear equations. So nature of solutions starts with case 1. Say for example, if I have two lines L1 and L2 given by A1x plus B1y plus C1 equal to 0, and L2 with A2x plus B2y plus C2 equal to 0 are the two lines intersecting at one point. That implies if two lines intersect at one point, then the solution is unique in case of this kind of a trend of the two lines L1 and L2. So if I have two linear equations in two variables x and y, then we say that the solution is unique if the two lines intersect only at one point. Unique is one and only one solution. That is, we get only one value of x and one value of y in case of this kind of lines intersecting. This being the example of case 1. Similarly, I take the case 2. If I have, say, two lines which are parallel, L1 and L2 given by the similar equations, but if the two lines are parallel, where we denote with L1 parallel to L2, implies the solutions So this implies with the general understanding that the two lines never meet. When two lines are parallel, they never meet, even at infinite distance. That means when two lines do not meet, there is no point of intersection and hence no solution. That implies the two lines L1 and L2 do not intersect and hence have no solution. They do not have solution because they do not meet. No intersection, no solution is how we understand this. Now the next is case 3, where there is a possibility that the line L1 and the line L2 coincide with one over the other. So such lines are called coincident lines, where this is coincident lines. In case of coincident lines, we see that one line passes through another line. That means they both intersect at infinitely many points. They intersect. This implies the two lines intersect at infinitely many points. The lines L1 and L2 are said to be passing through each other infinitely many times, and hence mathematically they are said to be intersecting at every point. Hence they intersect at infinitely many points, and therefore we get infinitely many solutions. One intersection, one solution. No intersection, no solution. Infinitely many intersections, infinitely many solutions is how we understand the nature of solutions connected to this, this, and this. That implies infinitely many solutions is how we understand the nature of solutions connected to the graphs. Cut.